Based on my research, the release of energy in a nuclear reaction is due to the explosive transformation of the missing mass. Specifically, the mass defect in a nuclear reaction explodes and is converted into a superthin form of matter. In fact, my studies suggest that a nuclear reaction releases energy because of this change in the state of matter. The exploding mass defect propels the reaction products at very high speeds. When these product fragments collide with surrounding matter, it results in the generation of a large amount of heat energy. In the following sections, we will explore how this theory can be verified. First, we will explore the spontaneous fission of uranium-238. The spontaneous fission of uranium-238 produces a variety of elements primarily within the mass number range of about 90 to 150, including krypton, Kr, xenon, Xe, barium, Ba, lanthanum, La, and strontium, Sr. On average, about 2 to 3 neutrons are released per fission event, with the most probable average being approximately 2.5 neutrons per fission. The mass distribution of fission products from U-238 is typically asymmetric, with a larger number of fission fragments having mass numbers around 95 and 140. This distribution follows a double-humped curve, indicating two distinct peaks corresponding to the lighter and heavier fission fragments. The total kinetic energy released in the fission of U-238 is approximately 200 MeV, distributed among the fission fragments and neutrons. Each fragment typically receives about 80 to 100 MeV of kinetic energy, while the emitted neutrons carry away about 2 to 5 MeV of kinetic energy on average. The emitted neutrons and fission fragments have distinct directional patterns. The fission fragments are emitted almost back-to-back due to conservation of momentum, whereas the neutrons are emitted isotropically but tend to show some correlation with the direction of the fission fragments. The mass and kinetic energy of fission fragments are inversely correlated, with heavier fragments tending to have lower kinetic energy. The directional emission of neutrons is correlated with the fragment velocities, showing a slight preference to be emitted in the direction of the fragment motion due to momentum conservation. The velocity of the fission fragments is inversely related to their mass, with heavier fragments moving more slowly compared to lighter ones. Velocities can be estimated using the kinetic energy relationship \KE equals \frac 1, 2, mv²2 \, typically in the range of 0.5 to 1.5 centimeters per nanosecond. The recoil of the fission fragments leads to significant kinetic energy transfer to the residual nucleus, often causing secondary interactions within the material. The recoil energy can be estimated from the conservation of momentum, where \p_text total equals p_text fragment 1 plus p_text fragment 2 \. The process adheres to several conservation principles. Conservation of energy ensures the total energy before and after fission remains constant, including the kinetic energy of the fragments, the energy carried away by neutrons, and the energy emitted as gamma rays. Conservation of momentum ensures the momentum of the fissioning nucleus is balanced by the opposite momentum of the fission fragments, resulting in a near back-to-back emission. Numerically, the mass distribution peaks are approximately at 95 AMU and 140 AMU. The average energy of neutron emission is around 2 MeV, with a maximum of up to 5 MeV. Each fragment typically carries kinetic energy in the range of 80 to 100 MeV. The recoil energy depends on the mass and velocity of the fission fragments, usually ranging from kF to MeV. Now we will analyze how this supports the exploding mass defect hypothesis. There are several key aspects or behaviors of the reaction products of the spontaneous fission of uranium-238 that could be considered evidence for the explosive event. The high kinetic energy of the fission fragments would indicate that a significant amount of energy was released in the form of an explosion, propelling the fragments at high speeds. The near back-to-back emission of the fission fragments would be consistent with an explosion occurring at the center of the U-238 nucleus, resulting from the conservation of momentum where the fragments are ejected in opposite directions to balance the momentum imparted by the explosion. The isotropic emission of neutrons, with a slight preference for alignment with the fission fragment motion, could be seen as a byproduct of the explosive event. where neutrons are scattered in all directions due to the violent nature of the explosion. The inverse relationship between the mass of the fission fragments and their velocities would suggest that the explosion imparts more kinetic energy to the lighter fragments, causing them to move faster. This behavior aligns with the concept of an explosive force distributing energy among the fission products. Significant recoil effects experienced by the fission fragments would indicate that a powerful explosion took place, imparting considerable kinetic energy to the fragments. The resulting secondary interactions within the material could be further evidence of an explosive force. The distribution of kinetic energy among the emitted neutrons, averaging 2 to 5 MeV, would suggest that they were also influenced by the explosive event, gaining kinetic energy from the explosion and being scattered in various directions. The asymmetric mass distribution of the fission products, with peaks around 95 AMU and 140 AMU, could be explained by the non-uniform distribution of the explosive force within the nucleus, resulting in a range of fragment sizes corresponding to the regions of the nucleus where the explosion exerted different levels of force. The directional patterns and correlations between the motion of the fission fragments and the emitted neutrons would provide further evidence of the explosion, indicating that the neutrons and fragments were influenced by a common force, the explosion, leading to related directional properties. The observed correlation between fragment size and velocity, where larger fragments move slower and smaller fragments move faster, supports the idea of an explosive event, with the explosion imparting varying amounts of kinetic energy to the fragments based on their size, resulting in the observed velocities. The total energy released during the fission would be consistent with the energy of the explosion, with the conversion of the mass defect into kinetic energy and the observed high velocities of the fragments indicating a powerful explosive event. The balanced momentum of the fission fragments, moving in nearly opposite directions, would be a direct result of the explosion's force acting at the nucleus's center, propelling the fragments away from each other. The measured kinetic energy of the fragments, around 80 to 100 MeV, would be strong evidence of a significant explosive force, as this energy must come from a powerful internal event. The estimated velocities of the fragments, derived from their kinetic energy, would further support the explosive nature of the fission process. For example, if a fragment with a mass of 100 AMU receives 90 MeV of kinetic energy, its velocity can be calculated to confirm the high-speed motion expected from an explosion. Here the key aspects and behaviors of the reaction products, such as high kinetic energy, back-to-back emission, isotropic neutron emission, velocity-mass relationship of fragments, recoil effects, and the mass distribution of fission products, would all serve as evidence for an explosive event during the fission of U-238. These observations align with the characteristics expected from an explosion, providing a comprehensive framework to support the hypothesis. When matter explodes, it changes to a less dense state. So when a missing mass explodes, the nuclear density matter is transformed into an extremely thin form of matter. Mass defect is a universal phenomenon occurring in various cosmic events such as active stars, supernovae, colliding neutron stars, and merging black holes. These events create mass defects on large scales throughout the universe. This leads to the important conclusion that space throughout the entire universe is filled with this diffuse form of matter. My books are available for purchase. Please visit Amazon.com/author/Adam.